So I'm Graham Stevens from KETIV, here to present a webinar on increasing reliability using Ansys simulation, and we're specifically talking about electronics reliability. So electronics are everywhere. You can see web-based devices. We're seeing automated cars. And as the web becomes more and more a part of our lives, we have smart devices, smart appliances, wireless connectivity. That's all becoming a part of the Internet of Things and affecting how we design products. And also affecting reliability of products. And so we are presenting this webinar to go over how we can improve reliability using simulation, trying to make them more intuitive, save customers money, lower costs over time, and have higher quality over the entire life cycle. And electronic reliability really is part of the universe of producing products. And so we're here to talk about how to improve reliability as we're designing products. And common electronics failure modes are usually due to environmental hazards. We have too much heat or thermal stress, dust, mechanical impact, cracks allowing water ingress, too much current, fatigue, contamination, or transient signals, EM signals interfering with the device. And these stressors that cause failures include high temperatures, electrical and mechanical shocks or stress during use, high humidity, contaminants, electrostatic discharge or material aging, or external EM fields, all as presented here on this slide. And electronics reliability is to try and mitigate these failure modes. And the ways we mitigate these failure modes is to somehow use protection schemes. And on this slide, I've listed a number of stressors, heat, voltage, current, etc. And then the typical ways that engineers protect against those failures. So on the heat side, we have thermal management. You use heat sinks to cool parts. You might shield parts from heat. For voltage, you might derate parts so that they'll withstand more voltage over time, or use surge or current overprotection circuitry. So listed here on this slide are just a number of different methods of protecting against these different stressors that shorten product lifetime, electronic product lifetime. And another key component of product life, electronic reliability, is, are you going to pass regulatory compliance requirements? So for some devices, especially where life is at risk or it's a high stakes situation, if I have an airplane, I need to make sure that that airplane flies, or I might have passengers. If a failure happens, you might have life at risk. Similarly for medical devices or automotive products. And so there's a trade-off between complexity and how complex something is, and what sort of regulatory compliance requirements you might have to pass. And so some of these are listed on the slide at the bottom here. We have safety, EMI or EMC, thermal cycling, vibration, halt testing. These are different, and some of these examples here are listed are different types of standards that you might have to pass to enable your product to be on the marketplace, on the market. And traditionally, companies have used a design, build, test, break it, fix it design cycle, as shown on the left, this business as usual design cycle. And these repeated cycles of did it work? And then we fix it. And did it work? Did we fix it? You go through a number of those until you get to a product that works, that doesn't break. What we're wanting to talk about here is the use of simulation to reduce that cycle and simulate and test for faults before you even build it at all in the first place. So you design the product, you simulate, you test for faults, you do a number of cycles to fix those faults, and then build it. And as a result of your simulation, we can severely reduce the number of test and fix cycles and reduce the product development cost in terms of the number of prototypes that we're cycling through, as well as reducing time to market. In addition, you also can improve the product as well, just in terms of its functionality, the number of conditions it can handle, and reduce warranty costs and potential for recalls. And some of the larger failures that we've seen in the marketplace on terms of electronic reliability is the Boeing 737 MAX grounding was due to sensor failure, and that cost $20 to $60 billion. And we've seen other larger electronic failures in terms of cell phones and ignition switches that, again, could potentially have been prevented through simulation prior to building the prototypes. And so a wide range of customers have benefited from Ansys electronic reliability solutions. And as I mentioned, the benefits include reduced design time, reduced product development timelines, and improved reliability and performance. So these are just a couple of examples. There are more examples on the website, Ansys's website, in terms of electronics reliability and simulation. But on the left is a Qualcomm cell phone, and using simulation allowed them to evaluate far more operating scenarios to be able to handle so many different conditions for dynamic power management, but just in general. And similarly, Danfoss used their AC motor drive design team to reduce the number of prototype builds and allow this particular drive box to be able to drive many more different devices than might have otherwise been possible in terms of operating scenarios. And then another academic company was looking at designing a cell phone and operating in different frequency bands and expanding its range of operation. And all of these are examples of getting there faster in terms of time to market, as well as reducing prototype build costs and design costs. And so when we think about electronics reliability, Ansys's simulation packages divide up the universe of electronic reliability into these sort of 5 relatively large buckets. So the first bucket is electrical reliability. It looks at current flow and signal integrity. Then there's thermal reliability. Is the part getting too hot or not? And how does that impact lifetime? Mechanical reliability allows us to look at if I do a drop test, is the electronic board going to survive? If I'm vibrating it and shipping, is it going to survive? So there are a number of different mechanical reliability tests and simulations one can do. And then you can do combined effects. So if I have, for this comprehensive multiphysics, if I take 2 effects and do them together. So a typical one is when I have current flow, and if I have high current, that might increase the temperature of the device in one particular area, and feedback, and that temperature could reduce lifetime, and then the high temperature could increase the current as well. So you can get feedback loops between some of these phenomena as well. And so Ansys can simulate both at once. And then finally, all of these particular reliability tests that one might do in terms of electrical, thermal, and mechanical reliability all can get fed into a larger or wider analysis of lifetime of both particular piece parts, and then taking the lifetime curves of a number of piece parts, whether that's part of a PCB, and looking at the entire PCB board lifetime, or whether it's a number of components of, say, a vehicle or other product, and pulling all the lifetime information for each of the components and getting the full lifetime of the vehicle. Ansys has a package that does reliability analysis where you analyze and try and predict what the mean lifetime of a product is. And doing that beforehand in the design stage allows you to zone in on, well, where are my low lifetime parts and how do I design those out or otherwise deal with them. And so diving a little bit deeper into the electrical reliability world, Ansys has packages that look at signal and power integrity of the board, looking at antenna performance in terms of simulations of S parameters and field plots, what kind of radiation is going to and from an antenna. We can also look at the PCB board itself in terms of how much radiation is it doing in terms of EMI, EMC. And so all of these different types of analyses are done with Ansys simulation tools to look at electrical reliability and particular electrical issues. And then on the thermal reliability side, Ansys has a number of packages that look at thermal reliability of the board or of a particular component, and can go at multiple scales. So it can look at the actual chip and its reliability, the solder balls, and how it's connected to the package. Can then go to the next level of the PCB itself, and then also can look at reliability of thermal reliability of an entire device, and model this with looking at the actual cooling, the cooling flow, whether that's by convection in a fan or whether it's by conduction through traces and so forth, and allow you to really get a sense of where do I have thermal reliability issues, where are the hotspots on the board, how is that going to affect my design. And then similarly on the mechanical side, Ansys has different packages of software that look at reliability and fatigue and life on the mechanical side. So looking at stress and strain of solder joints, coatings and pottings and underfill, a number of different types of tests that you might have to pass, real world tests in terms of a drop test or moisture ingress tumble test. And all of these conditions and types of tests can be conducted at a very detailed level with a finite element model to predict what's going to happen before you actually design the parts. And then, as I mentioned before, one of the advantages Ansys' software has is that all of these different pieces are integrated together so that you can actually run simultaneous simulations and mix and match. So look at electrothermal feedback loops between thermal properties of materials and stress and strain with how the electrical performance of the device. So we can again look at how does the hotspots on the board affect the stretching or the strain of the board as it arises. How does the electrical device impact temperature and vice versa? And all of this can be done, all of these pieces of software talk to each other and can be integrated into a full package to get a much more full picture of this type of device. And then one of the newer things that Ansys has been focusing on is also doing system level modeling. So if I have a PCB package and I'm say 1,000 parts in a car, if I have to do a detailed analysis of each one of those 1,000 parts and try and run a simulation, it gets to be very complex and onerous relative to computation. And so a newer technology or method of doing system level analyses is to do take a look at the very detailed situation and create what's known as a reduced order model that only tracks a few variables, but still captures the particular reliability phenomenon that you're looking for, whether that's current flow or stress, and model it effectively, but do it much faster. And then that reduced order model can get fed into other reduced order models for other components, and you can actually start looking at full system reliability with similar integrity. And then finally, taking a slightly deeper look at the reliability physics analysis that Ansys offers called Sherlock. This is where we start looking at the individual components and what's the mean lifetime of all the capacitors on the board, all the resistors, and then look at all the different components on the board. And now we can start looking at which pieces we might need to improve how we're either design around them or substitution. There's a number of different ways to improve component reliability, and build up to what is the lifetime of the board, and take a look at that prior to building the board using wide bulk curves, and then look at standards compliance as well. Will it meet these standards? And do that at the component level, the board level, or the system level. And so just to try and make this a little bit more concrete, I wanted to show a mechanical reliability example. And so this is an example of a PCB board where we might have a system on chip that's sort of shown in this dashed line area here. All of that's been sort of shrunk to one chip. And while the connectors that are in the gray boxes here are pretty well defined, they get placed first and they're necessary for accessibility and use. Knowing where we want to put the system on the chip, the SoC, which tends to generate a fair bit of heat, is sort of a question mark. How do we, where do we put this so that it will survive mechanical shock? And so this example is showing these blue boxes here with question marks. Well, there are a number of different places we could place this large heat source on the board. And now we want to take a look at, well, how is that going to impact stress and strain, thermal stress and strain as in operation? And so following through on this example, this graph that's shown on the right is actually out of plane displacement map, not a temperature map. So it looks like temperature, but it's not. So the red is showing where you're having higher mechanical stress and strain, where the board is warping out of plane. And we could simply plop it in the center and place it in the worst possible location. And the analysis that was run shows that within 2 years, 5% of your products are going to fail due to that high stress and strain situation. And so obviously we need to figure out what to do about it. What are some other protection schemes we could use to mitigate this issue? And so this next slide shows a number of different strategies one could use. So one strategy that was on the left here is we could move the component and just shift it over and see if that helps relative to the support locations in the four corners. Another possibility, and that improved lifetime slightly in terms of this, but maybe didn't quite make it on the 10-year lifetime we're looking for. We could add some more supports and see if that helps. And so this middle box here shows the results of adding more supports in the middle. And that again improved the lifetime somewhat, but we're still seeing 5% failures after 10 years. And then finally, a third solution is to add some sort of underfill to the SoC. And so the Ansys simulation that is shown here is the potting region, just sort of the inputs for the underfill. And we can sort of see that now the red line has gone to almost zero in terms of product probability of failure has gone to almost zero, and so the underfill solution looks to be the correct one, or at least improve lifetime quite a lot. And then, so that was an example of just looking at one particular aspect of mechanical reliability in terms of where am I going to place components. There are many others in terms of some of the shock tests that we were shown before, etc. And I wanted to just sort of outline here, show you an example of more of on the reliability testing side, the overall Sherlock package. Some of the inputs and types of tests that we can use to test packages, and then how one might score some of those. So on the input side, we can look at temperature cycling, we could look at earthquakes, we could look at vibrations, potholes, collision, thermal shock, harmonic vibrations. So there's a number of different potential input conditions that the product might experience over its lifetime. And so in the Sherlock package, you would define, okay, I have, typical product cycle for a truck, and what kind of vibrations does it have to handle. And then on the output, we get these lifetime prediction curves, a combined curve as well as broken down, looking at different potential failure modes. So I could look at solder fatigue only, or semiconductor wear out, random vibrations, mechanical shock. So the number of these different potential analyses you can run to look at lifetime. And then you can also, in addition to looking at just the mean lifetime, you can also score your product against a number of these different types of analyses. So if we do a fatigue analysis, how does the product compare against a scorecard of fatigue? If we look at harmonic vibrations, how does that work, etc. So there are a number of different conditions here that we can rate against. And of course, these also correspond to compliance requirements in these particular areas as well. So one question we got was, how does Sherlock do the combination of thermal and mechanical loading? And the answer to that is you would do the analysis. So say you have a solder ball that you're looking at thermal stress in the solder ball as current goes through, and you're also looking at mechanical loading of that solder ball, so you have a vibration test. And so relative to that combined test, you would do a more detailed analysis in the thermal and mechanical simulation parts of Ansys, and then feed the results of that analysis into Sherlock, essentially. So Sherlock will take the outputs of that kind of analysis of, I have this shock condition and this temperature profile, and does it hit those and survive, and it'll take the results of that test to create the lifetime Weibull curve, so that it's fully integrated. Any other questions? All right, well, with that, I think we will stop, and thank you so much for taking the time. And please join us again next month as we dive further into electronic reliability, based on the poll results that we just got. Thanks so much, all. Appreciate it.